Okay, so we are discussing today, resuming our discussion on RNN transducers. A quick recap. This is the original paper which we uh, are discussing. We saw so many applications of that, or so many problems which can be solved by this approach. Basically, all sequence tasks could be ASR, TTS, machine translation. We discussed how it is different from a CTC model. So basically, input can be of any length, output can be of any length, and we are also modeling the output dependencies, means the output dependency of, let's say, yt on yt minus 1, yt minus 2, etc. Like language model, means modeling the syntax of the language. Now, we discussed some mathematical notation. Our input is x, output is y, and in ASR, x is a sequence of audio frames. Let's say every entry is spectrum or MFCC features, and then our output is string. Basically, it's a sequence of tokens, and these tokens could be characters, words, word pieces, etc. Now, how do we represent? So we add a symbol called phi in the output. This phi is basically, what does it mean? Phi, uh, one at a time. Please raise your hand. A blank. And it, what does it indicate? Move t by 1. Go from t to t plus 1. That's what it indicates. And this combined vocabulary, a sequence which is uh, which is made up of this combined vocabulary is called A. It's called an alignment sequence. Similar to the notion of path which we had earlier. But earlier in CTC, the length of the path was equal to the length of input. But here, that constraint is not there. Uh, Rather, we have seen that length of the path is equal to length of, you remember, input plus output. I think that will be coming sometime soon. So we discussed what is Py given x in terms of Pa given x. So A is the path which starts at t equal to 0, u comma 0, u equal to 0. If I know the ground truth, just put your ground truth here. PASS, let's say that's our ground truth. And you start from this particular node. You start from this node and you end up in this node, which is right outside your capital T comma capital U node. And then you basically map all such paths to your label sequence or Y sequence. So probability of the sequence Y, output Y given X is given by sum over all paths which when you apply B operator, they give you Y, right? And then we discussed the model architecture. So you have an F is like an encoder, which means it's like a transcription model, which transcribes your input directly into the uh, token classifier. Right? This is a token classifier. Output is of length k plus 1. K is your vocabulary size. For English, what is k? So 26 characters plus blank, 27. Blank means this is a space bar. So the separator between words. So 27. And okay, of course, if you can add punctuation marks, it will be further more, but let's stick to only small caps characters and space bar, 27. And then this length is 27 plus 1, 28, because you also have phi. So 28 is the length here. And this is called the transcription model. And then you have G, which looks at your previous outputs and tries to predict the next output. Something like your language model or your LLM. What LLMs do, they look at the text and try to predict text. So this is a text regression, looks at your previous text output and tries to predict the next whatever symbol, word or grapheme, whatever. And this H basically combines both these outputs and gives you the final output, right? means it's called self-regression output plus the transcription output that is combined by H. And we saw some applications like in ASR, in TTS, and in translation, in handwriting recognition. So all these applications are basically sequence to sequence transduction tasks. Then we discussed a little bit maths of G network. So our um, you can always start your Y output with a phi symbol. You assume that you're sitting at phi, and then you from there you start producing more things. And we discussed some details like the output of Y is one hot vector, which means a softmax uh, vector. And in this case, Y basically you use all zero vector to represent phi, but you can use the other way also. But this is only in the input. In the output, you can't use all zero vectors. We discussed the reason that softmax cannot give you all zero output. The sum has to be one. So GU is my k plus one length vector. And so what is G basically? It's an RNN or an LSTM model which looks at the previous sequence, tries to predict the next output. And the transcription network is simply a mapping from input to output. Input is the audio, output is the text. And it could be a bi-LSTM. If we use a bi-LSTM, it means that we are, since at every time instant, we are looking the entire audio and trying to predict my output text. So it's globally, you are looking at the entire sequence at every prediction. It's not a causal model, huh? It's a non-causal or a-causal model. Okay, then H is simply it combines both of them. How does it combine? Add them up and apply softmax. So treat F and G outputs like logit outputs and then add them up element by element. There are k plus 1 elements there, k plus 1 elements there. Add them up and that becomes your final logit output, and then apply softmax nonlinearity, you get the probability scores. And these are the actual probability scores which you will be using for token probabilities. Once you have token probabilities, then you can find the path to find your path probabilities, right? Token probabilities to path probabilities. How do you do that? You start from this point, right? Your U is phi and you're looking at the first frame, and then you see what do you predict. And depending on the predictions you take, let's say this path will have, at here you have some prediction, here you have some prediction. You just multiply them up along the path, and that gives you the uh, path probability. Path probability is basically product, but take this product carefully. You have, because it's state dependent. What is the time instant here or time frame here, and what was your previous outputs? Both matter. So t comma u both matter. Since you have only single sequence here, so u is sufficient to tell you. Huh? So u tells you about your previous sequence also. Okay, then that's it. Then you basically, and then we defined some forward variable and backward variables. Why? For the purpose of differentiation. The same way we did in CTC. So how do we define the forward variable? It's basically alpha t comma u, probability of all valid paths. When I say valid, it means they map back to y, the original y, whose probability you want to find, right? So all valid paths reaching the node t comma u, let's say this is t comma u, starting from 1 comma 0. And basically you can compute it very efficiently using, what is it called, the dynamic programming, right? So which means you initialize it, and then you have an induction function or how to calculate tth value if you know the t minus 1th value, or t minus 1 comma u minus 1th value. So that kind of uh, you can regress or recursion. And what is the initial value? We saw that when you start, you always start at this node, so probability is 1. So you start with alpha 1 comma 0 is 1. Then you recurse, and what is the recursive formula? Alpha t comma u is given by this form. We derived it in the last class, so I will not do it again. And what is py comma x in terms of alpha t comma u alone? So if alpha t comma u you compute at the last node here, that will be the path. That is the probability of all possible paths which give you y as your output, which basically map to y when you apply b operator. And so basically you just find the probability of this reaching this node, which is alpha t comma u into probability of phi given t comma u. And similarly, you define the backward variable, exact same maths, you initialize it and then you recurse in the reverse direction, similar formula you derive, and that's it. Now we come to the new stuff. How do you train this model? So we were dealing with the model, playing with the model, seeing how things are computed. Now we are ready to train the model. So for training, so this is your model. So I have drawn the model here and some equations I have written just for reference. Now, what is the loss function which you want to minimize? What loss function you want to minimize or maximize? Either way. Uh, all path probabilities for the known output. Yes. So it's likelihood, right? You want to maximize the likelihood of the known y, probability of y given x, and the theta parameters of the model. You want to maximize py given x, comma theta. So that's what you want to maximize. So, or in the other words, you want to minimize the negative of log likelihood. Minimize the negative log likelihood. So log likelihood is p y star given x. Y star is the ground truth, right? And x comma y star is coming from your training data, right? Is this clear so far? Nothing new? You understand all the terms, right? E is the expected value computed over this random variables, x comma y star. These random variables are basically sampling from training data. And using Monte Carlo, you know how to compute this, right? And log py given x is known. You know how to compute y star given x from the model. We have already discussed that. Did we discuss that? No, we didn't. Okay, we will discuss now. Okay. Now the question is, when you maximize it, you will basically, what do you do to maximize it? How do you maximize the loss function? Differentiate and then equal to 0. But then this is very complicated. It won't be 0 easily. Then you use iterative methods like gradient descent, etc. So we need the gradient. What is the gradient? So what are our models here? H has no parameters, right? H is simply a deterministic uh, sum them up and exponentiate and then normalize, right? So H is just a parameterless operation. Where are the parameters? In the F model and G model. We want to train both F and G. Huh? So let's first differentiate L with respect to F. What is F? FKT basically, huh? Because FK, K is the output node. There are capital K plus 1 nodes, so indexed by small k, and small t is the input time frame, right? So you have FKT is the output of this model, right? We have discussed this. I hope this is visible. Is this visible at the back? Then come in the front. You can come, no problem. Please. It will be easier. Okay, they are too afraid. Fk comma t, huh? So basically it means F output of F at tth time and at the kth node. So it's a scalar. Scalar or vector? Scalar. Fkt is a scalar, it's a logit value basically. So how do you differentiate L with respect to Fkt? You will just apply chain rule, right? So derivative of the term inside with respect to F, which will be basically 1 upon P into derivative of P with respect to F, right? 1 upon P is easy to compute. You know how to compute P. Now, how do you compute derivative of P with respect to Fkt? That's the question. Uh, the equations are there in front of you. Would you like to compute what is derivative of P y star given x with respect to Fkt? And you know the formula of P y star given x, right? Sum over all paths whose inverse image, the B inverse image, or the B image maps to Y. I mean, B inverse of Y, right? All the paths in the set B inverse Y, you sum over them, and then you compute the uh, path probabilities. So it should be something like this. So P y star given X derivative with respect to FKT is uh, now this P y star given X will, if you look at here, it is basically product of P k given T comma U, right? Product of P k given T comma U along the whole path, right? So what you have done here is that you have differentiated P y star given X with respect to P k given Tu, and then same chain rule, right? So you want to, so okay, so you know that this P y star given X is a function of P k given Tu, right? This P k given Tu. So let's uh, apply chain rules, split them apart, and then let's look at both of these terms individually or separately, right? So now, how many of you agree with this form? So here you see P k given T comma U, you don't know U, right? But you know that it will sum over all the U's. That's why you're summing over all U's. Means you know that you can take value 0, 1, 2 up to capital U. That's why you are summing over all possible U's. Okay. Can you spot any mistake in this formula? So what's happening is P y star given X is a function of P k comma T comma U, P k given T comma U, right? Uh, so it makes sense that you split it apart in this way, right? So what is the problem here? Okay, so let me help here. How many of you remember differentiation of a softmax function? Derivative of a softmax function. Okay, when you have a softmax function, let's say you have k plus 1 nodes or some number of nodes. If you differentiate this output, sorry, um, let's say this output is your ground truth, huh? This output is your ground truth. Let's say K1 node is the ground truth, huh? K1 node is the ground truth. What is the derivative of the loss function with respect to K1 output? It will be something non-zero, right? What is the derivative of loss function with respect to some other node, some K2 node, which is not K1? What is the derivative? It will also be non-zero. Why? Because in the denominator, look at the denominator here. So here in the denominator, you have all possible values of k. Derivative is not 0, right? So therefore here, when I'm trying to differentiate this P y star given X with respect to FKT, I know that the internal variables P, K given T comma U, this K need not be same as this K. It can be different also, because even if they are different, even then the derivative will be non-zero. So the right form becomes like this. So you say, I think we have discussed in the past also, when you differentiate something, let's say if you have, you want to differentiate something with respect to pk, let's say, then, and this is internally dependent on some k, don't call it as same k, call it as k dash and differentiate. If they come out to be same, it's well and good. If they don't come out to be same, you are still on the right path. So it's safer to call it as k dash. So that's why we here sum over all k dash, because uh, all these k dash um, are possible. The derivatives won't be zero, right? Okay, so we'll come back to this. Let's first look at these terms individually, and then it will make more sense to you. So what is let's compute first this term. What is p k star, sorry, p k dash given t comma u derivative with respect to f k t, right? So the terms are here. So I want to compute derivative of this term p k dash given tu, right? This is the term with respect to fkt, which is here. What is the answer? It's simply the softmax formula. Could you compute? Could you compute derivative of p k star, sorry, p k dash given tu with respect to fkt? Formulas are there in front of you. Done? It's very easy. Just start doing it. So there is some maths involved. So I would recommend write. When you write, the connections become clear. It's very simple maths, but just that too many equations. That's why you may get confused. Find derivative of pk given tu with respect to fkt, or k dash given tu, and then find out if this derivative is 0 when k dash is not equal to k, or it is non-zero. That you can find out. Then you can discuss amongst yourselves. This is true and k is not equal to k. But k equal to k. What if k is not equal to k? Can you repeat that sentence? Then I think I found my right answer so far. Okay, so it's very easy, very simple derivation, differentiation. Just that maybe you're afraid of the terms, but it's very simple. So this is what we are trying to do, right? So first write the value of pk dash given tu in terms of fkt. It's simply the softmax applied to fk dash plus gu k dash, right? Do you agree with this? So it's simply the derivative of this. This term is pk dash given tu. All of you agree with this? Now see here, I have used k dash here and k double dash here and k is here. It's important to differentiate or to distinguish between these three k's. Right? Now find the derivative. So it's possible that k dash is equal to k. It is possible that k dash is not equal to k. Both these cases have to be considered. So when you do that, somebody's already found it, you get this form. It's simply exponential. So let's say you apply division rule, divide by b square, let's say denominator square, and you multiply with denominator, derivative of the numerator minus derivative of denominator and keep the numerator, right? When you apply that, you simply get this form. And this delta k dash appears because the numerator term, see the denominator term will always contain k, because k double dash you are summing over all possible k's. So somewhere k term will appear, but the numerator term may or may not contain k. It will not contain k when k is not equal to k dash. But when k is equal to k dash, then numerator also has k term. Right? That's why the delta comes there. So it's p minus or pk dash times 1 minus pk, where this 1 is 1 when only when k and k dash are same. All right. Okay, so you can easily verify this. Let's go to the next part now. The other term, which was we discussed this already. Yeah. So this term we have already seen, derivative of, oh, okay, this with g. Same thing happens with g also, right? The same thing, you can differentiate the p y star given x with respect to g k comma u, and but you see here now, you are summing over all t's, because here p y star given x is a function of both t and u. U is known, specified, but t is not specified, so keep that sum here. And then rest of the things are follow the same logic which we discussed. And so we have basically seen how to compute this term, and this term we will see in a while. This term also similarly, you basically know this is the thing you get. Now let's come to the other term, which is common in both f and g, which is derivative of py given x with respect to the output of your neural network mixed. So pk given t comma u, the output of h module. Huh? The h model gives as output pk given t comma u, right? Now you want to compute derivative of py given x, right? The total probability of that sequence with respect to the output of your final h network. So here we need to use the forward backward variables, right? Let's say you specify your t comma u as this node. If you specify it as this node, then you want to compute the uh, derivative of probability of all possible paths, all valid paths which pass through this node, right? So for that you need alpha beta. So you know that py given x is basically given by alpha at this node into beta at this node. Did we discuss that? In the CTC algorithm we did. In this algorithm also did we do that? No? Did we do it? No? Okay. So it's basically with the same logic, you get this py given x is simply alpha into beta at this node. But then, okay, yeah, I think it will come. So, but then, uh, you know that, sorry, probability of all paths, all valid paths which pass through this node is given by alpha into beta, is alpha tu into beta tu, right? Now, what is the py given x then? I repeat. So what I'm trying to say is that p probability of all paths all paths or all valid paths through the node u comma t or t comma u is given by alpha tu into beta tu, right? Now tell me what is py given x, which means all possible paths, not just the paths from that t comma u node, but all possible paths. What is the probability in terms of basically alpha beta? What will that be? If you take all t and u, then you are overcounting the paths. Let's say one path passed through this node, and then it went here and then went here. And if you sum them up, it's like you are summing the same path twice. And like that, you will be doing it so many times. So you're overestimating it by many, many times. Overall use. If you find all those u's, let's say if you take any particular t and over all the u's, then also you're overcounting, because I may go through this path and then I will go through this path, then I will go through this path. Basically, I will be same path, means anything which is coming out of this door can also enter this door and cross this door. Like anything crossing this node can also cross this door. So what you have to do is you have to find mutually exclusive doors. Earlier, path was always in this direction, right? So all the doors which were in the vertical section, vertical cross section, they were mutually exclusive, because if you are passing through this door, you can't pass through this door, right? All paths which are passing through this door, they can't pass through this door because they are mutually exclusive doors. Now here you have to find the mutually exclusive doors. So find what are your mutually exclusive doors, which means you are sure that if it is passing through this node, then it cannot pass through this node. Where is that node? Diagonal, along the diagonal, right? If you're passing through this door, let me use another color pen. If you pass through this node, you can never pass through this node. And you can never pass through this node. And you can never pass through this node and never pass through this node. So if I have drawn here 5 nodes, if you are passing through any one of them, you can't pass through the other doors. Can you see that? Are you sure now? So these are our mutually exclusive doors. What is the equation of this? What is the equation? T plus u is equal to constant. It's a straight line, right? 45 degrees line, straight line. T plus u is equal to constant. That's what we do here. Sum over all, T plus u is equal to constant. N is some constant. And alpha t into bu. Basically, alpha t into bu is a sum of one set of valid paths through one door, t comma u door. Like that, take all tu which are mutually exclusive on that line, and you sum over them, you get all paths. Is this easy? Right? It's easy, right? You know how to find probability through one door, and you know mutually exclusive doors. Sum them over. That's it. Okay. Okay. Now, what is is there any limit to the value of n? N can be minus 2. Can n be minus 2? No, because t is positive number, u is uh, either 0 or positive, non-negative number. So n cannot be less than, what is the minimum value of n? 1, because t is 1, u is 0, that is the minimum value. So n has to be greater than or equal to 1. What is the upper limit? Pardon? Minimum of? Why minimum? Let's say you take this door. So here the value of t is capital T, 6, and u is 1. So 6 plus 1 is 7. So it's more than minimum of t and u. What is the upper limit? Yeah, u plus t. U takes its maximum value, t takes its maximum value, you are at this node. It cannot be more than that. Okay, right. So it has to be between 1 and u plus t, including both these boundaries also. So this formula is true for any value of n between 1 and u plus t. Okay, so now let's come to the derivative part. So now we found the paths. Now taking derivative is easy, right? So basically you have to take the derivative at one particular node like this, and then sum over all these doors. That's it. So, okay, now tell me, I'm repeating the formula here. Py given x, the numerator is given by this form, sum over all mutually exclusive paths or through all possible doors of alpha into beta, alpha tu, beta tu. Alpha tu is given by this recursive formula, beta tu is given by this recursive formula. Tell me what is the derivative of this with respect to pk given tu. So what is the derivative of this term with respect to pk given tu? K can take any value, valid token capital out of capital K tokens or phi. So look at the formula of alpha. Do you find anywhere pk given tu? It's only t minus 1, u minus 1, but nowhere tu. Look at the formula of beta. Do you find anywhere ptu? K given tu. Where? Pardon? P phi given tu and P y give uh, yu plus 1 given tu, right? Yu plus 1 is basically a character or a token. So probability of this token given tu. So when k is equal to ytu, yu plus 1, that's where this term will be same as pk given tu, right? So can you now find the derivative? Just write down what you just now said. Okay, I know you can do it. So it's like this, huh? So alpha t comma u, it is independent of pk given tu. So alpha tu is as it is, it's a constant. Then inside you have beta t comma u, its derivative basically. So look at this formula. So this is basically beta t plus 1 comma u, that's constant, into when k is equal to phi, then this term will be 1. So that's why delta k comma phi plus beta t comma u plus 1 times delta when k and yu plus 1 are same, then this term is 1. Easy, right? Just linear derivative of a linear function. Done? Okay, that's it. Once you are able to compute py given x with respect to the model outputs, now you can compute the entire loss function. Right? There is no term left in loss function which you don't know. Easy, right? So that's it. Training can be done in this way. Now we come to the next part, which is inference. Okay, you trained your model. Now how do you do inference? Um, so this is our model. Now I have an audio sequence given to me. Let's say I'm saying something pass or something, pass or passerby or whatever. And then this is the output sequence generated by the model. Uh, Now I want to generate that audio sequence, that output sequence which has the maximum probability, right? And I can do it in a greedy way also, but greedy approach is not the optimal approach. Means you just look at the whichever token has the highest probability and just plug it in there and then move forward in that way. But that is not the best decoder. Hmm? Can we do something better? So ultimately we want to find argmax with respect to y of py given x. Whichever y has maximum probability, that's my estimated y. The network gives you pk given tu, right? That's clear. Pk given tu basically is the output of h. So if there are k nodes here, so you basically get pk given tu output. Now Uh, the question is, how do we find py given x, which has the maximum value? For which y is this probability maximum? That's what you want to find, right? Uh, there is a small catch here. What is the catch? If my model is outputting, let's say the correct output is PASS. So P has a high probability, but it's also possible B has a high probability. Pass and BAS are quite similar. So PER has a high probability. BER also may have a higher, like maybe not as high as P, but let's say somewhere significant probability, right? Now, which one will you take? If you say I will take greedy approach, always I will take P, then you are suboptimal. You want to find the, so you want to also consider, okay, maybe B also should be considered. But now when you go to the next step, you have to run two models. One model will be conditioned on P, other model is conditioned on B. And then again it will branch out. Let's say pass and bas. Let's say next character is A or A, pass and bas. Then again, so you got two possibilities. Either after per you got A or A. And now, okay, you just want to consider both of them. And then, but again, it will branch out, right? You know, to now you have to consider these two paths plus those, let's say after ba also you have ba and bay. So two paths there. So it became four paths now. So number of paths will be exponentially growing. I only considered the case when you have two possibilities. Let's say if you have 27 plus 1, 28 possible outputs. So it is growing as 28. Then again at every node you have 28, 28 into 28. Then 28 cube, 28 power 4, 28 power 5. It will be exponentially growing problem. So how do you manage that? So that's why the inference becomes difficult. So that's what I'm saying here. Uh, so your gk comma u, that's the model which depends on previous outputs. And if the outputs are multiple, then gk comma u will be basically expanding, exploding. So during training, it was not a problem because I know exact path, exact output sequence. There was only one sequence, but during inference, it is a problem. So how do we tackle that? So we have to track the previous outputs also, and then it grows like this. So now here I have written the notations as well. In the beginning, you are sitting at u equal to 0, sitting at phi. So you're sitting at phi. Now, what is the output of your model? Let's say the input sequence you are at time t equal to t. It could be 0 or 1, whatever. Let's say you are at time t equal to t. And your model outputs, there are 28 neurons, some value for every neuron, some probability for every neuron, right? So let's say I took three possible paths. I can take 28 of them, but just for the space constraint, I've taken three of them, per, bur, and per. So I'm saying pass, bas, pass, could be any of them. So per, bur, and per I have taken. Now, as soon as I move to this u, let's say u becomes u plus 1 or whatever. So I get, now here my model will be computing pk given t comma p, which means the previous string. I cannot simply say u because my previous string is not same in all the cases. So I have to write the whole previous string. My previous string is per here, right? Now I look at the output nodes. Let's say there are two nodes, A and A. Now, if I move to the A path, I get the model now will be emitting probability of k given t comma, the previous string is PE, whereas here the previous string is PA. And like that, if you see here, P k given t comma BE, k given t comma BA. But what if it emits phi? If let's say somewhere it emits phi, then what will it be? Let's say the path taken is the path here during inference you took the path F and then phi. What will be the output of this network? Pk given t plus 1 comma f. You will not say t comma f phi because in the phi you won't input phi again. So you will just say p t plus 1 comma f. All right, and like that. And you basically this here you started with one value, then it became 3, then it became 6, and it will keep growing. Means this is a simplistic example. it will grow like 28, 28 square, 28 cube, 28 power 4. It will be out of control. How do we optimize? How do we, I would say, track? How do we track the problem? What do you suggest? Very obvious solution. Okay. If you put a threshold, then it is difficult to know what value should I choose, right? Because let's say uh, uh, threshold may be a little difficult. Let's say if there are 20 entries above threshold versus there are only 2 entries above threshold, then the range will vary too much. No? It's possible that there are hundreds of entries above the threshold because you have limited compute power. Let's say number of CPUs is fixed. You can only track at the most, let's say, n number of paths. That's the upper limit of on the number of paths you can track, because otherwise your CPU requirement will be outside your bounds, right? So how will you manage that? So instead of putting a threshold, put a limit on the number of paths you can track, right? That's equivalent, right? So instead of saying that I put my threshold here, just say I will take, let's say, at most top 10 paths, not more than 10, right? So that's what we do. It's called beam search. You only track top W paths. W is some number you fix, let's say 10 or 100 or 1000, whatever, depending on your computing resources. And you track only the top W paths. So let's say when you start from here, 5, and then you went to 3 branches. And in these 3 branches, yeah, let's say W is 3. Let's say in this example, I've taken W is equal to 3. So it is within my bound. So okay, I take all 3 values, means I accept all 3 paths. When I am here, it again expands into 3 and 3 and 3. Now my limit is 3, so I only take the top 3 paths. This one, and this one. And here these paths I discard. I don't track further. Only the top 3 paths I have taken. And now once I'm here, again expand them, and you found here this path has a, you compare all, what is 9, all 9 of them you compare. So you'll find, okay, one path, this is the highest probability, and these 2 are also high probability, and others are low probability. So only take those 3 paths and discard others. That's the method of beam search, that you track only the top W paths. Easy, right? There is a, in the paper there is a simple code given to implement it programmatically, but I think that is not required. If you understand the maths, that's how it is. So that's it. So that's all. So that's all about RNN transducer. So now you know what is RNN transducer, how to train it, and how to do inference with it. What else do you need? Right? Okay, you need some codes. Here are the codes. Nemo has RNN transducers again. You can get the codes from these links. Right? So this first code, it is basically having codes for both CTC and RNN transducers. And then this one is a an intro, or basically a tutorial on transducers from Nemo team again. That's it. Any questions? It was a bit mathematical today, so take your time, digest it, and then next class you can tell me